Hello, my name is Anyawasin. Today I'll be talking about calculus. I will walk you through the history of calculus, monotonicity, local maxima and minima, first derivative test, and the application of those. Well, when was calculus invented? In ancient Greece, calculus was used mostly to tackle a problem like geometry. However, calculus was most developed in the 17th century by Isaac Newton and Gottfried Leibniz, and has great contribution to science nowadays. Let's move to the monotonicity. A function is monotonic when it always increases or decreases within its domain. In other words, when the plot goes along the axis, the value of y is either greater or lower throughout the domain. For this graph, we call it a strictly increasing function. For the second graph, it is a strictly decreasing function. But for the third one, we see the increase at the beginning, but then we'll see a drop, so it does not always increase or decrease. This function is not monotonic. We can also consider a plot within a specific interval. The first function is strictly increasing on its domain. The second has the same behavior, but the third one is not monotonic in its domain, or we can call it non-monotonic function. However, if we consider the interval from 0 to infinity, it is strictly increasing. On the other hand, within the interval from minus infinity to 0, it is strictly decreasing. Let's see the relationship between derivatives and monotonicity. The derivative can help us determine whether a function is monotonically increasing or decreasing within the considered interval. Just a reminder, the first derivative of a function is the slope of a specific point in the domain. If the slope of the function is more than 0 for all members in the interval, the function is strictly increasing within that interval. Conversely, if the slope of the function is less than 0, the function is strictly decreasing within that interval. Let's see the second example is a linear graph of which the first derivative form is 1, so it is strictly increasing. The third one, we can divide it into two intervals. On the right-hand side, the slope is always more than 0, so it is increasing. On the left-hand side, the slope is always less than 0, so it is decreasing. If the point in a function is the highest among its neighbors, that point is the local maxima. If the point in a function is the lowest among its neighbors, that point is the local minima. The x that gives local maxima and minima can be called critical points. First derivative can help us determine whether a critical point is local maxima or minima. When the slope changes from positive to negative, it is a local maxima. On the other hand, when the slope changes from negative to positive, it is a local minima. If it doesn't change the sign of the slope, it's neither local maxima nor minima. Let's see some application. Local maxima is mostly used in finding the maximum of things, for example, the height of a stone thrown in the air. Local minimum is mostly used in finding the minimum quantity of things like cost. I have a challenge for you. If I would like to create a box with an open top from square cardboard with side 12 cm by cutting a square of side x from each corner and then folding along the dotted lines, what's the x that gives the highest volume? Well, the volume of the box is length times height. where the length is 12 minus 2x and the height is x. So we obtain the formula of the volume now. Then we transform it into the first derivative form. To find the critical point, we let the first derivative form equal to 0. Now we acquire the critical point at x equal to 6 and 2. How do we know which one is the maximum or minimum? We can use the first derivative test. For the critical point at x equal to 6, we consider x a little bit before and a little bit after. The slope of x equal to 5 is minus 36, and the slope of x equal to 7 is 60. It can be seen that the slope changes from negative to positive. Hence, x equal to 6 is the local minimum. Let's consider the neighbor of x equal to 2. The slope changes from positive to negative. Therefore, there is a local maximum, thus giving the maximum volume of the box. Thank you for watching.